Okay, thank you. So yeah, before I start, let me say that this is a joint project of a lot of people, and we have yeah, it has like lots of different parts which are done by different subsets of these people: Laurent, Mateusz, Tim, Martin, Andrei, and Yaroslav. But I think maybe we'll write at least one paper all together. But there are also like lots of related questions which are done by different subset of these people. Okay, and yeah, and this is very much in progress. We still have some results, but a lot of questions are still open. Okay, so let me try it very well. Let me start like very basic. So let me talk about inversion of matrices for like real quick, just to set up some notations. So I'll work with projective space of n by n matrices. So it's projectivization of C n square. And I always will denote, well, later I'll work with, mostly in this talk, I'll work with space of symmetric n by n matrices. And then this will be projectivization of projective space of different dimension. But during my talk, I always will denote by capital N the dimension of this space I'm working with. Well, to start with, it will be capital N is equal small n square, but later it will be something else when I pass to symmetric matrices. But it always, capital N is always a dimension of the space I'm working with. And okay, so we want to study the inversion map, which is a which we view as a birational map of this projective space to itself, which sends, if you have invertible matrix, it sends it to inverse, but it of course has some indeterminacy locus, which is a set of like locus of matrices of rank less than n. And specifically, we want to study the graph of this map, which is, or like more precisely, the closure of a graph. Well, this is the closure of set of pairs A inverse, whereas A is invertible matrix. So this is a subvariety of product of projective spaces. And the basic questions we're going to study is what is the cohomology class of this subvariety. Okay. So yeah, so what a cohomology of product of a projective space? Let me very quickly remind you. Well, the cohomology ring is generated by two classes. One is pullback of a hyperplane class on the first factor, and another is a pullback of hyperplane class on the second factor. And of course, if I intersect this hyperplane with itself, or pullback of this hyperplane with itself n plus 1 times, I should get 0. And it turns out that this gives a complete description of cohomology ring of product of projective space. So it's ring generated in two variables, modular like these relations T1 to N1 plus capital N plus 1 equal to 0, and T2 to the capital N plus 1 is equal to 0. So to determine the class of a subvariety of P to the N times P to the N of codimension N, it's enough to know the intersection indices, intersection numbers of X with hyperplanes with T1 to a correct degree, T1 to a monomial in T1, T2 of correct degree. So I will call multi-degree of X of index I D minus I, well, the intersection index of X with first pullback of a hyperplane for the first factor taken into degree I, and all together intersect with a pullback of hyperplane taken from the second factor to the degree D minus I. And well, and just why is it enough? Well, by Poincare duality, you can write the class of X as a following polynomial where degrees, like multi-degrees, are exactly the coefficients of your monomial in T1, T2, or like opposite coefficients. Okay. So yeah, let me now come back to this original question. So if we have this graph, it's a variety of Pn cross Pn. So like as we noticed before, what we're interested in is like in this bi-degrees of this graph. So let me slightly reformulate this question, and let me do it by saying the following thing. So to compute this by degree, it is the same as to take L, generic linear subspace of codimension I, and then the bi degree of my graph gamma I is equal to the degree of L inverse, whereas by L inverse I just denote the closure of inverses of all matrices from A. So, well, all invertible matrices from A. So if I take all invertible matrices from L, I take their inverses and I take the closure of this set, and this I denote as L inverse. So this is also a subvariety of Pn. So instead of by degree of my graph, I can look at the degree of this subvariety of Pn, which I denote by L inverse. And yeah, so as I mentioned to you earlier, we mostly will work actually with symmetric matrices in this talk, but kind of this question makes sense in like all three settings. Like you can ask it degree of this inversion map of. You can ask about this cohomology class of a graph of an inversion map on the whole space of matrices, or on symmetric space of space for symmetric matrices, or anti-symmetric matrices. And then you will work either with Cn tensor Cn, or symmetric square, or lambda square, or exterior square of your space, original space Cn. And always, well, I will not say anything about anti-symmetric matrices, but when I will talk again, let me repeat, when I will talk about symmetric matrices, then by capital N I will mean the dimension of symmetric square of Cn. And if I talk about just all the matrices, again by capital N, I will mean the productivization of Cn tensor Cn. And let me just give some notation. So let me define this, well, degree of L inverse, or by degree of a graph, or corresponding cohomology class of, or corresponding coefficient of a cohomology class of the graph, just by this function phi of In. So I is the codimension of my space L, or like index one of the indices of by degree, and N is the space of N by N matrices. Okay, and so what we're going to discuss is like how to compute this phi of In. Okay, yeah. So let me pass to this one approach to do this, which uses C-star action on Grassmannian. So for this, let me take V. Let V be a dimension n vector space over complex numbers, and let V star be its dual vector space. And let me consider this action, which defined on the first vector, it scales everything just by t, and on the second vector, it scales everything by t inverse. So it's very simple C-star action on this space. It has just two weights, and this action, well, it induces also a C-star action on Grassmannian, and of n planes of V plus V dual. And well, just it's little technicality, but of course, if I take t equal to -1, then t inverse is also equal to -1. Then like -1 acts non-trivially on the space V plus V dual, but of course on Grassmannian, if I have a plane, well, it will be just multiplied by -1, so the action will fix a plane. So my element -1 of C star acts trivially on Grassmannian. So we take we take a corresponding transitive action, which is an action of a factor torus C star by -1, which is also C star. And like let's denote this action by resultant action by delta. Okay, so how this action is related to the inversion map? Well, first, let's notice that delta has exactly two isolated fixed points in the Grassmannian n of n planes inside of V plus V dual. And these two fixed points are the subspaces V and V star themselves, because of course they're fixed, and it's easy to see that they're isolated fixed points, and it's easy to see that they're, well, you can describe the fixed point loci, and there are no more isolated fixed points. And moreover, the tangent spaces at these points are naturally well identified with homomorphism space, from, well, one from V to V dual and another from V dual to V. Moreover, a generic C star orbit inside of a Grassmannian connects two isolated points, and moreover, a C star orbit at each of these fixed points has a well-defined tangent direction. Well, it doesn't have well-defined tangent vector, but it has well-defined tangent direction. So this defines as a birational map from projectivization of a tangent space from tangent space at V to the Grassmannian to the tangent space at V dual to the Grassmannian. Again, how this map works? Well, we take a generic C star orbit, and we look at two tangent directions in one isolated fixed point and another isolated fixed point, and we get this correspondence between tangent directions, and this turns out to define as a birational map. Okay. Are there any questions so far? Okay, yeah, so let me just notice that this map is birational indeed, because generic orbit indeed has two limits into two isolated fixed points, but there are non-generic orbits which can start in one isolated point, but actually can have another limit, not go all the way to the other isolated point, but can kind of stop somewhere in the middle, and that's why it has some indeterminacy locus as well as. Okay. And like relation, how this related to inversion of matrices? Well, very easy, because if we choose some basis of V and its dual basis of V dual, then we can identify these tangent spaces, because like this was homomorphism spaces with actually n by n matrices. And this is like a little proposition that under this identification, if we really do this, well, this birational map which we constructed using the C star action is nothing else as just inversion of matrices, if we identify both tangent spaces with spaces of matrices. So we gave kind of geometric interpretation of this inversion space of inversion of matrices. Okay, yeah, and like to do the same thing on the space of symmetric matrices, we need to work a little bit more. Well, namely, what we have to do is we need to consider a natural symplectic form on this space V plus V dual. And for this symplectic form, we have a Lagrangian Grassmannian. So what is Lagrangian Grassmannian? Well, it's a subset, actually. It's a subvariety of the Grassmannian n of n planes inside of V plus V dual, but we take only such n planes, only isotropic n planes. So n planes such that restriction of our natural symplectic form to this plane is identically equal to 0. Okay, and again, this is standard that tangent space to, well, it's easy also to see quite explicitly that tangent space, well, the action of C star, first of all, preserves on the action C star of C star on V plus V dual preserves form omega. Therefore, the induced action on the Grassmannian of n planes preserves the Lagrangian Grassmannian. So, so we have this Lagrangian Grassmannian also comes with this restriction of action delta, and the tangent spaces to the two isolated fixed points, which are only two, again, like V itself is a Lagrangian plane, and V dual is also a Lagrangian subspace of V plus V dual. So both of the isolated fixed points are still belonging to Lagrangian Grassmannian, and they're the only isolated fixed points there. And we can similarly construct this map F delta, so it should be also birational map. And then the tangent spaces now can be identified with a space of symmetric matrices. So the corresponding birational map will be the inversion map between symmetric spaces. Between spaces of symmetric matrices. Okay, so I told you already that we have two isolated fixed points, but let me tell you, let me describe you all of the fixed points of this C-star action we constructed on a Lagrangian Grassmannian. So for this, well, it is really easy to see that like the action we defined. So if I have a plane in Lagrangian Grassmannian, or like even in usual Grassmannian, so it's C-star invariant if and only if I have like, I can choose a basis for L such that all my basis vectors either belong to V or V dual, or like more invariantly, you can formulate that the dimension of intersection of L with V plus dimension of intersection of L with V dual is equal to N. Well, okay. And also, if I fix any subspace K inside of V, just inside of like my half of my V plus V dual, I can complete it to a Lagrangian plane by considering space K plus orthogonal to K intersected with V dual. And it turns out that this is always Lagrangian. It's also like very easy to check. And and this correspondence is 1-to-1. So if I have, so this gives us a description of all C-star, all fixed points of C-star action. And this description is very easy. It just says that this fixed C-star fixed locus of Lagrangian, like of C-star action Lagrangian Grassmannian is a disjoint union of n components, and each component can be identified either with Grassmannian IV or Grassmannian like n minus I V dual, which are also like naturally isomorphic. And in particular, you see that only two components actually isolated points. Others are like have some higher dimension. Okay. Okay, so yeah. So why are we doing this? Why are we doing like this geometric interpretation of? Why do we want to interpret like this inversion of matrices geometrically? Well, because this interpretation kind of suggests to us that we can use a space of C-star orbits on Lagrangian Grassmannian to resolve the inversion map. So yeah, let me formulate this as a theorem. So there exists a smooth projective variety X, which contains an open part parameterizing generic C-star orbits on Lagrangian Grassmannian, and this moduli space of orbits comes with two natural projections to projectivization of a tangent space at first isolated fixed point and projectivization to a tangent space at the second isolated fixed point. And this variety X resolves the birational map F delta. So that means that the diagram which contains like these three spaces X and two projective spaces and maps between them pi 0, pi n, and F delta is commutative. And like on the open part where all the maps are well defined, it's actually an isomorphism. So as formulated, this theorem is maybe not very interesting because, well, you can always resolve indeterminate, like you can resolve all the singularity. But what is interesting is that this space X has a modular description and very concrete modular description. And let me tell you what is the description. For this, let me remind you about moduli space of stable maps. So Kontsevich defined this moduli space of stable maps. So these are stable maps of genus G curves with n marked points to a variety complex variety Y, where we fix some class beta in its second homology. So this moduli space very roughly parameterizes maps of this curve C with n marked points to Y, so that the image, like push forward of fundamental class of C, has class beta in well, the image of C is some curve inside of Y, so complex curve has to have some class in second homology. Well, of course, some components have come with multiplicity, so the condition we want is that push forward of fundamental class of C is equal to our fixed class beta. And so it turns out that such moduli space exist. So it's representable by the Lin-Mumford stack, and the fact that it is our map is stable basically means that the map should the map itself, not the curve, but the map itself should have only finitely many automorphisms. So if you, maybe it's more familiar, like spaces, moduli space of curves are slightly more familiar object, and there you have this condition on how many fixed points you might have on each component. Like each component of degrees of genus 0 should have at least 3 special points, and each component of degree of genus 1 has to have at least 1 special point. But here, actually, components might have less points if map F is not contracting the component. So the whole map itself can have only finitely many automorphisms. And as a moduli space of curves, the moduli space of spatial maps has a natural compactification, which parameterizes stable maps of curves with, the smooth part actually parameterizes stable maps where C is a smooth genus G curve, but in the compactification you might have some reducible curves, but when worse singularities you might have a simple self-intersections. And condition of stability is what I said. Okay. So it turns out that we can realize our space X as a connected component of fixed point locus of M00 of Lagrangian Grassmannian, where we fix class beta to be the generic, the class of a generic orbit closure. Again, we have some action on Lagrangian Grassmannian, and this action leads to an action to the its moduli space of stable maps. Because if I have like a map, I can act on the image of this map I can post-compose this map with an action of C star, and this defines me an action on M00. And then, if I want to parameterize orbits, this is exactly corresponds to my map being an invariant point of this Kontsevich moduli space. And of course, class beta we should fix to be generic class of a generic orbit. And you can, using this description, you can very kind of precisely or very concretely describe the points of this moduli space, the points of X. And namely, they kind of look like zigzags, or more precisely, they're chains of C star orbits. So generic orbit will start in one fixed point, isolated fixed point, and will end in another isolated fixed point. But we also might have some chains of orbits which go to some intermediate Grassmannian, and then from intermediate Grassmannian they go all the way to the end, or maybe we can have several breaks or whatever. The only thing which we can never go back, because this is a condition on the cohomology class. So there's a chains, and if I label my components if I label my components from 1 to n+1, then I can only increase when I go from one component to another. So so these ones have very precise description, the point, the space is not just it has some modular interpretation, but it also you can see very precisely what the space is, what are points of the space. Okay. So now let's come back to our original problem. So we want to compute these numbers phi of in. And now we can relate this problem to actually intersection theory on this space X. And the way it's done is the following. So right. So if you remember what we need to do, we need to compute this bi degree, which comes from intersection of hyperplane, which is pulled back from the first factor of projective space to the power I, and the second factor of projective space to the power capital N minus I. So instead of doing this intersection with a graph, of our inversion map, we can also do this intersection with on X itself. So we can perform this intersection on X, and we'll get the same answer as before, because X exactly resolves our inversion map. And it turns out that you can actually do this calculation, and you can do it using equivariant K theory on this space X. Well, that comes from so actually on Lagrangian Grassmannian we have a bigger torus. We have an action of a bigger torus, namely like torus C star to the n, which acts on V. And it turns out that under this action of this bigger torus, the space X has only finitely many sorry, what I wrote is well, it's not, well, maybe it's correct, but it's not quite what I wanted to write. So what I wanted to write is that this bigger torus C star to the n has only finitely many fixed points on X, on our moduli space X, and it turns out that we can actually find describe all of these fixed points. We can find characters of C star to the n action on the tangent space to X at these fixed points, and we also can write explicitly classes of like pullback of H0 and pullback of Hn in this equivariant cohomology. So we can use the localization theorem to give very explicit expression for these numbers phi in. But just because I want to give you several hours way to compute this number, like in this talk I'll give you several ways to compute this numbers phi in. I will not spend too much time on how, like I will not say anything about like kind of formulas you obtain. I just say that this is can be done very explicitly. Okay, are there any questions so far? Okay, so if no, then let me move on, and let me now talk about complete quadrics. Okay, so I'll start with something which is maybe sounds a little bit non-related to original question, but it will be related to it very soon. Okay, so yeah, so like this classical enumerative problems, they go back like to Schubert, I believe, and like the kind of questions Schubert wanted to study is the following. So assume we have a space of quadrics, smooth quadrics in Pn, and we want to find the number of quadrics which satisfy certain geometric properties, certain geometric conditions. Like for example, number of quadrics which pass through some number of points and tangent to some number of hyperplanes, like which are fixed, like stuff like this. So the problem with this is that the space of smooth quadrics is a homogeneous space. It's easy to see that it's a homogeneous space of PSL n+1, which is factored by PO n+1. But well, unlike the classical Schubert, well, unless in the case of Schubert calculus, where we work where we study enumerative problems on like planes or like also geometric like planes which satisfy certain geometric conditions, the parameter space of planes is a Grassmannian, which is a compact space. So we can make like the Schubert calculus precise by just working with a cohomology of Grassmannian or Chow ring, whatever is more convenient for you. And since Grassmannian is a compact or complete, intersection theory is nice. But the space of quadrics, of smooth quadrics Q, is not compact. So when you do intersection theory, like you might have some problems with it because like the number of intersection points is not fixed under, like if you choose like the same, like a different variety which represents the same class, it might have some different number of intersection with another variety. So like you need some compactness to do this. And well, where is an obvious solution for this? Well, we need to consider some compactifications of our space Q. But the problem with this solution is that there is no like one best compactification which works simultaneously for all types of enumerative problems. And actually, you can if you formulate certain enumerative problem, then you need to find the compactification which will suit well for this particular question. And actually, in this case, it can be done. And motivated by this, De Concini and Procesi, they defined the so-called ring of conditions. And this ring, which remembers all cohomology of all possible equivariant compactifications of Q. And in particular, they showed that all enumerative problems can be done as a computation inside of this ring of conditions, well, which is hugely infinite, but kind of more down to earth. What they really showed is that for any type of enumerative question, you can find a suitable equivariant compactification. So you can really find the compactification of Q, which will suit well for this enumerative problem. Okay, but more precisely, well, coming back to, they actually showed it not just for space of quadrics, they showed it for more general class, for like so-called spherical homogeneous spaces, but that's not maybe very, well, I will mention spherical varieties a bit later, but also very briefly, so it's not super important maybe for this talk if you don't know what are they. But let me talk a little bit more about space of complete quadrics. Okay, so what kind of enumerative problems we might be interested in? Well, we have on the space of quadrics, we have n geometric divisors. So to define them, well, we have n natural geometric classes, but we actually can define the representatives in each class by doing the following thing. So let us fix a flag of subvarieties, of flags of planes inside of Pn, full flag of planes, f0, f1, etc., fn, with dimension of fi equal to I. And then the divisor li, so there is a slight shift of indices because it will be a bit convenient later, but the divisor li contains all the quadrics which are tangent to fi minus 1. So fi minus 1 is I minus 1 dimensional plane, and li is a subset of quadrics which is tangent to fi minus 1. Turns out that this is a divisor, and of course, if you change the flag, like the divisor will change, but it will have the same divisor class. So by fixing the flag, you actually fix the representatives of this divisor class. Well, slightly you can formulate, like you can construct this divisor slightly differently. Well, the choice of a flag defines as a Borel subgroup inside of PS7 plus 1, and it turns out that these flags are exactly, well, that this Borel subgroup has an open dense orbit inside of Q, and the complement is a union of divisors Li. So Li is, so the complement inside of Q to the open Borel orbit is a union of n prime divisors, and like these divisors are exactly Li's. Okay, so now what is the space of complete quadrics? Well, this is, so yeah, before we just talked about homogeneous space, which was not compact, but now the space of complete quadrics X is a specific equivariant compactification, and what is good about it is that it's suitable for intersection of divisors Li. So in other words, if you have an enumerative problem about quadrics being tangent to certain linear planes inside of your Pn, well, this enumerative problem can be interpreted as intersection of some divisors Li's, monomial of divisors in monomial in Li's, and the space of complete quadrics is a compactification which is well suited for such intersections. So let me define it a bit better than just this. There are different ways to construct it, but one way is the following. Well, for a symmetric matrix, so we work with a projectivization of W is our space. We work with W is the space of dimension plus 1, so PW is like our Pn we work with. So for a symmetric matrix, A inside of S2W, we define like lambda k. Oh, sorry. So we define this. So let's say a subscript k, to be equal this wedge k of a, and this is an operator on wedge k of v. Oh, so many typos here in this such a small thing. Can I? Oh no, sorry. Let me actually. So this should be w. And also, yeah, and this is, I just denote this by, oops, maybe. Oh no, oh no, no, no. So this wedge k, wedge power of a, I'll denote it by ak. So in particular, and this is an operator of lambda kw, of wedge kw. In particular, like this an, which will be wedge n of a, is a matrix of a dual quadrics, or equivalently, it's actually is an inverse matrix up to the scaling. And then we can define the space of complete quadrics X as the closure of these tuples from A1 to AN, where again each AK here is lambda KA. So this is a point in the product of projective spaces like this, as is written, and they take tuples of all such things where A1 is invertible. Because if A1 is not invertible, some of these wedge powers might be equal to 0, so they're not well defined as a points in projective space. So we take only invertible matrices, we take all the tuples defined. So A1 defines all others. So we take all the tuples of these matrices, and we take the set of them and take the closure. And it turns out that X is a smooth equivariant quantification of Q, and this is the space of complete quadrics. Okay. So why do we talk about complete quadrics here? So now I'm ready actually to relate this to our original problem. So it turns out that the space of complete quadrics is equivalently isomorphic to a moduli space of C-star orbits on Lagrangian Grassmannian. So the variety which I constructed in the first part of my talk as some C-star invariant locus of concatenation moduli space is actually the same as the space of complete quadrics. And also the classes which we consider, which we consider there to define this, to find this function phi in, have natural, they're very natural in terms of this complete quadrics, namely their divisors L1 and Ln on the space of complete quadrics. Okay, so this indeed is a different way to look at the whole story. So this gives us another way to compute these numbers phi in. So it tells us that this phi in is equal to L1 to the I and times Ln to the capital N minus I. And, or in other words, this is nothing else as just a number of quadrics in Pn which pass through I given point and tangent to N minus I given hyperplanes. So this is a kind of enumerative question people were studying for like centuries. There is and kind of this approach also gives us some possible answer to this enumerative question. So far we just did some reformulation, but what's the actual answer? Well, one way to answer this question is using spherical geometry. And again, let me not spend too much time on this, but basically there is a Brion-Kazarovsky formula, which is a generalization of famous Bernstein-Kushner-Cohomology theorem, and basically it relates the intersection number of hyperplanes, hypersurfaces on the spherical variety to the integral of certain homogeneous polynomial over a polytope. And again, maybe let me just tell you one word, like integral of a homogeneous polynomial over a polytope, it sounds kind of not very explicit, but it turns out that you can actually, this gives you some very explicit answer because the polytope itself you can write, in this case, you can write very explicitly the polytope over which you integrate. The polynomial which you integrate, you can also write very explicitly. And now you have very explicit polynomial, very explicit polytope. So the answer is like the integral of 1 over n hour. Still sounds a little bit tricky, but it turns out that it's also a formula due to Brion. It turns out that if you triangulate your polytope, you can really compute this integral very explicit over each simplex. You can compute it very explicitly. And then, of course, if you have a triangulation, you can sum up over all simplices. So it's complicated expression, but all these steps can be done, and you get some kind of answer for this as well. Okay. Any questions about this part? Okay, so if now, let me talk a little bit more about some more intersection theory of this space of complete quadrics. Okay, and well, first let me, I told you a number of reformulations, but let me tell you like a little bit about some results which we got. So there was like this conjecture of Sturmfeld and Euler. So they were interested in this function phi in because it comes from algebraic statistics, and it's equal actually to so-called maximal likelihood degree of the linear concentration model, which I will maybe not talk too much about today, but they're interested in this numbers. And what they conjectured is that if you fix I, and if you increase n, then this numbers phi in is a polynomial in n of degree I. And this theorem is known in some number of cases. So for a equal to 1 and 2 and a equal to 3, oh sorry, this should be I, not a, but whatever. So this is known. And this is basically like, this is not hard, and already in Sturmfeld and Euler they proved it for a equal 1, 2, and 3, and here are the polynomials you obtain. And for a equal to 4, it's a result of Chardin, Azimuth, and Euler from 2015. There they compute this algebraically using this algebraic intersection theory. They use excess intersection theory. And it turns out that actually it was known before for statisticians, and it's a result of Stuckrad from 1992 as well. But up to now, these were only cases which were known, and what we actually were able to show. And this is not the date. This is the first. If I didn't make a mistake, this is should be the first letters of people who worked on this. So we were able to show that this is actually a polynomial for any I. And what is interesting, well, we also get some recursive formula for these polynomials, which allowed us to compute them explicitly for quite big I think 43, if I'm not mistaken. But what is kind of funny is that number phi in doesn't make sense if n is small, because well, I should be less than dimension of space of symmetric n by n matrices. So if n is a smaller than, if I is a big, like if we fix I and we start with n which is smaller than some bound, which is easy to compute, well, these numbers doesn't really make sense. But it turns out that the polynomials we compute, they actually have 0 values for, so this is a polynomial not just starting from some place where this number is starting to make sense, but it's really an almost polynomial starting from 0. And it gives 0 values all the way up to the place where n, the dimension of space of symmetric n by n matrices becomes larger than I. So it's like these polynomials are kind of nice. They have like lots of like linear factors, and also if you factor these linear parts, which I just said, where some nice properties like these polynomials might have. Maybe, I don't know if, yeah. I can tell maybe later a little bit about what we noticed. It's, yeah, we didn't prove anything yet, but it seems like we have a number of conjectures about like these polynomials. Okay, and yeah, so let me just say a couple of words how you can get this. So for this, you need like a third approach to like a third way to compute these numbers, which is also, well, it's like they're all kind of related, but this is slightly different one, like a new one. So yeah, so let me first describe the Picard lattice of X. So we have, I already told you that we have these classes L1, Ln. Well, the way I told you, we have these classes inside of the open part, but of course you can take the closure inside of the whole X. That's what I mean here. But we also have n divisors, which are complement to the dense PSLN plus 1 orbit. So if you remember, X was an equivariant compactification of the space of smooth quadrics. So, so it has some boundaries, let's say at infinity. And it turns out that these boundaries at infinity, we have exactly n prime divisors. And let me denote these divisors like S1 to Sn. And also we have, yeah, so this proposition is kind of classical. So it says that L1 up to Ln are independent, and they do generate the Picard of X. And moreover, like you can see like relations between Li's and Si's like this, like they're written as Si is equal to minus Li minus 1 plus 2Li minus Li plus 1, where we just take L0 and Ln plus 1 equal to 0, just formally. So that like relations, like they're slightly different in the end. And there are several ways to see it. First of all, it's very classical. It's maybe was even known to Schubert, but also like you can see it through spherical geometry description, spherical geometric description of it. There are lots of ways to see it. Yeah, and let me just write it down. So we can reverse these relations, and then we'll get L1 equal to n times L1 is equal to this expression in SIs. And I believe this should finish with Sn, not Sn minus 1. I know. Yeah, sorry. So so the relation is actually written for PSLn instead of PSL minus 1. So you should add 1 to all the coefficients, and you should add Sn in the end. Sorry. This is a typo, but it's not super important. Okay. So why do I talk about this? Well, because it turns out that we actually, instead of evaluating L1, Ln, it's easier to evaluate, to rewrite it in a different way and then evaluate it in a different way. Well, by applying just this above relation, we can take one of L1 and we can rewrite it as a linear combination of SIs. And then like this monomial L1 to I, Ln to the n minus I, capital N minus 1, which is a phi I, well, n plus 1. This monomial is actually equal to the like sum of these things. It's like sum from k equal to 1 to n of k times sk, L1 to I minus 1, Ln to the n minus I. Oh, so many typos. This is not really phi, this is phi multiplied by n plus 1. But it's also not very important. I mean, what is important that like we can write phi as a linear combination of sk times some monomial L1 in L1 and Ln. And it turns out that this, this thing, sk times L1 times Ln to some degrees, turns out to be easier to evaluate than the original monomial L1 times Ln to some degrees. And the reason for this, well, is because the divisor sk has a very nice description in terms of this first moduli problem. If you remember, I described my variety X as a space of stable maps, and points of X were like the zigzags of C-star orbits, and Sk exactly corresponds to zigzags. It contains zigzags which pass through Grassmannian KV. So it has like a very precise definition, and in particular, it comes with a natural projection to Grassmannian KV. And moreover, Sk is not just comes with a natural projection, it's also birational to the total space of a vector bundle, very precise vector bundle, which is S2U plus S2Q star. whereas U and Q are tautological and quotient bundles on my Grassmannian. So I have very precise kind of birational model to this SK, and like this actually allows us to relate. Well, now if I want to perform like evaluation of this monomial SK times L1 to some power times Ln to some power, well, I can actually, since I have this SK, so this is the same as pulling back like this L1 and Ln to this divisor SK. So on SK, I need to perform this computation. It turns out that I can really boil down, like this computation boils down to certain computation in terms of Segre classes of these two bundles, S2U and S2Q star. And this relates the original problem to very classical Schubert calculus. And by playing with this classical Schubert calculus, it turns out that it's possible to show the polynomiality of each of these monomials, and therefore of the whole linear combination, which is the thing we were interested in from the beginning. Okay, so yeah, let me finish here, and yeah, and if you have some questions, you can ask.